Adding vectors, scalar multiplication of vectors, and unit vectors. So I'll tell you right away the part of this that's complicated. This is all it's very straightforward. Okay, but the part of this that's complicated comes when we talk about these two different ways to represent the same thing. This is kind of an annoying thing that happens kind of often in math, especially parts of math that have really clear interdisciplinary connections. Meaning, this part of math is so closely related to like physics and engineering that kind of those different like disciplines like to use different conventions for the same thing. The procedures are all the same, but the notation just looks a little different, which is annoying. Okay, but if you can kind of wrap your head around the fact that these two different ways we're going to represent the same idea, they're the same thing, you'll be fine. So there's something called the position vector. We talked about vectors, and we talked about how these arrows here, these directed line segments, the arrow indicates the direction, the length of the line segment itself represents the magnitude and direction, two pieces of information that constitute what a vector is. Um, they look like this, right? And if you just overlay the coordinate plane like we've been doing, you can see pretty clearly that you can see this point on this little triangle that's formed is 6, 3. And you can even go so far as to say, hey, vector M, it's 6, 3. And we use this notation here, this notation in these little arrows, where the first piece of information we give is a horizontal component. In fact, look, the coordinate point 6, 3, right? It's 6 in the x, 3 in the y, 6 in the x, 3 in the y. In this diagram, vector M is what's called a position vector. And the only thing that makes it a position vector is that it's at the that one of the ends of this line segment are at the origin. So we can go 6 to the right and 3 up, and that's the unit vector 6, 3. Now, vector M is still 6, 3 regardless of where it is. Okay, so what I mean by that is I could move, I don't know why I can't move it here, but I could move, hold on a second. So I can move vector M, right? I can move it over here. It's still 6, 3. Just by virtue of it being right there, it's called a position vector M. This idea of a position vector only allows us to more clearly understand another topic that we'll get to in a minute. Okay. Now, because we can call this vector, so vector h for example in this case is not a position vector, but it's still on the coordinate plane, and we can still quantify it and give it the same kind of notation where we've got, all right, how different is it in x, right? This is very basic. This is like the distance formula. It's not even a distance formula. It's just trying to find a change in x, change in y. So it's 2 to the right, so positive 2, but then 4 down. Right? The direction of this is important. If it was flipped, right? If we had vector h go in that direction or something, it would be different. Okay, but in this case, it's this way. So it's 2 to the right and then 4 down. So 2, negative 4. If we wanted to know then what was vector r, well, we know the constituent vectors of vector r. We added m and we've added h. So if we added up all of the x's, so the 1, 2, 3, 4, 5, 6 x's for vector a, and the 1, 2 for vector for vector m, and then the 2 for vector h, that'd be 6 total for vector r. Sorry, we did 6 and 2. 6 plus 2 is not 6, it's 8. And if you do the same thing for the y's, you go the 1, 2, 3 up for vector m, and then the 1, 2, 3, 4 down for vector h, you end up with negative 1. And that's also evident here. If we make r a position vector, it's just the coordinate points of the endpoint of this. Okay. Now, it's important to understand that, yeah, vector h is 2, negative 4, and in this specific orientation, in this specific location, it's called a position vector, but that doesn't change the fact that vector h is still 2, negative 4. Like it's 2 to the right and 4 down, okay? That's how we can quantify that. If this seems like it's x and y coordinates or horizontal and vertical components of this like triangle that we could potentially draw here, hey, that's a very good connection that you made, because that's really what vectors come down to, is trigonometry and drawing right triangles. before we get more into that, though, um, when we talk about multiplication of vectors, there's three different things we could be talking about. We could be talking about this right here, which is scalar multiplication. We could be talking about something called a dot product. We could be talking about something called a cross product. We're going to briefly talk about dot product. We're not going to talk about cross product in this class. But scalar multiplication of vectors is very common, and scalar multiplications is just like if you had scalar multiplication of anything. Hey, what is a scalar? It's just a number. It's just one piece of information. It's 2 in this case. Vector is 2 pieces of information. But if I wanted to like say what is vector v plus vector v, like this is how we add vectors, tip to tail, right? So vector v plus vector v, that's the same thing as 2 vector v. Just like if you had x plus x, that's just 2x. Okay, so scalar multiplication essentially just means we're multiplying the vector by 2. So we have now 2, it's 2 times as far in the x, 2 times as far in the y. For example, vector h from the previous examples, if we multiply vector h by 3, well, now this 3 vector h is way down here somewhere, right? Way off the screen. And it would make sense then, hopefully, that all you would need to do is essentially distribute this 3 into the different components of vector h. So the horizontal component of vector h2 and the vertical component of vector h negative 4, multiply 3 by both of those things, you get 6 times negative, 6 negative 12. That is what 3 times vector h is. Okay, now, just like when we dealt with right triangles on the coordinate plane, it was always the case that the hypotenuse of those triangles was positive. Okay, yeah, maybe it's going off. Maybe we have a triangle like, let me just refresh your memory here. So here's like a really poorly drawn coordinate plane, and here's like a circle centered at the origin, and we had this right triangle right here. Okay, oof, it's pretty bad. Yeah, maybe this hypotenuse is down over to the left, so it's like over in the negative. This whole triangle's in quadrant 3, which everything's negative there. But the hypotenuse is still positive, okay? Because it's a magnitude. It's a distance, right? This distance is positive. So we have this magnitude is not no coincidence that the magnitude and the absolute value signs are pretty similar, okay? Now, specifically, there's a specific kind of vector that's called a unit vector. A unit vector is simply a vector with a magnitude of 1. So if we wanted to know what the magnitude of this vector would be, all I would need to do was think about, okay, what is this vector? What is this talking about? All right, well, here is a vector, okay? Sorry, here's a coordinate point, and we'll draw that vector real quick. So 3, 4. So we're going to go 3 to the right and then 4 up. So this vector is like that, right? Now, what's the magnitude of that vector? Okay, hopefully you see that this is just a right triangle here. So if I wanted to know what the magnitude of this was, I would just say use the Pythagorean theorem, a squared plus b squared equals c squared. That is exactly how you find the magnitude of any vector if you're given it in this kind of notation where you have a horizontal and vertical component. Okay, so it'd be 3 squared plus 4 squared. So 9 plus 16 is 25. So 5, right? The magnitude of this vector would be 5. It's simply the Pythagorean theorem. Okay. Now, there's such thing as a special unit vector. Actually, you know what? We didn't talk about this. What do I have to do to get a unit vector in the direction of vector v? Okay, well, what the heck does that mean? How would I know, like, what does that mean? Let's see. If I had a vector like this one vector off in this direction, right? Well, what would I do there? Like, I wanted to essentially know how do I get that piece of information? Well, we'll get into that in a minute, and We'll come back to that. So for now, special unit vectors. Okay, there are certain unit vectors, specifically a unit vector in only the horizontal direction. Okay, so like literally, this is a vector. This is a special unit vector I, a special unit vector j. The components are we have 1 in the horizontal, 0 in the vertical. Vector j, we have 0 in the horizontal, 1 in the vertical. Those have magnitudes of 1. Okay, that is like really that's an important thing to understand. And sometimes you'll see the term unit vector I, unit vector j. in higher level math and into like vector calc and stuff, sometimes we hear this called I hat because it has this little hat on it, and J hat because it has this little hat on it. But essentially, it's just a unit vector I, unit vector J. So you can break a vector up into horizontal vertical components. We've talked about that. And so you can represent a vector in this other way. So this vector v, if we called it a comma b with these little greater than and less than signs, or less than greater than signs, you can also represent it like this. These are the same notation. This is what I was talking about, how there are two different ways to represent the same thing. Okay, this and this are literally the same. Okay, they are not interchangeable. You can't like say, oh, this is, AIBJ or something like that. That doesn't work. You can't like take different parts of it. You can either be using this notation or this notation. They're the same thing. They're telling you the exact same information, but they're different in terms of different like disciplines kind of use them differently. Okay, so I kind of prefer this method because you can really actually break down this idea and look at it like this. Okay, so we have for vector m, same vector m we've been working with, it can be broken down into like these 6 unit vector i's and these 3 unit vector j's. So instead of 6, 3, we write it as 6 I hat plus 3 j hat. That's unit vector m. Notice how this notation has a comma separating the horizontal vertical components. This notation has a plus sign. So if vector m was down over here somewhere, then it would be just minus 3j hat, be 3j hats down. Okay, this is also useful when we add vectors. So we've been able to add vectors before. We just added the horizontal components and added the vertical components. But now we're really adding up all the I hats, right? All the i's. So there's 6 here, 3 here, and adding up all the j's. There's 3 here and 4 here. So 6 plus 3 is 9 I hat. 3 plus 4, 7 j hat. It's pretty straightforward. Hey, if we wanted to do if we wanted to do these operations, you could pause the video here and just make sure you can get these answered, right? But if I'm adding vector q to vector s, I'm just going to add the horizontal components. 3 plus negative 5 is negative 2, and negative 5 plus positive 10 is positive 5, right? Those are the negative 2 I hat and 5j hat plus 5j hat. If I wanted to do 2 times vector s minus 3 times vector q, I would first have to multiply vector s by 2. So I take 2 into this negative 5 and 10. So 2 times vector s, it would be negative 10 comma 20, right? Or negative 10 I hat plus 10 j hat. And then negative 3 times vector q, I have to multiply this negative 3 into these. So negative 3 times vector q would be negative 9 I hats plus 15 j hats. Then you just combine all your I hats and j hats from your these two terms, and you'll get this. So I would encourage you to pause the video, work through that problem to see if you can get that. Okay, now same deal with magnitudes, right? If I wanted to know the magnitude of vector r, well, it's not the magnitude of vector m plus the magnitude of vector n. That's not the case at all. What it is just if you take all the I hats, right? Imagine there's this larger right triangle here. Some good color to use. Let's see. So there's this larger right triangle, right? This one. Well, what's the Pythagorean theorem here? We have all the horizontal components. It's all the i's. We have all the vertical components, all the j's. This practice here of drawing, of like kind of sketching in these right triangles is going to come in extremely handy when we get into some of these applications of vectors later on in our unit on vectors. Okay, so if you did that one, you'll notice that the magnitude of that was square root of 130, okay, because we had 81 plus 35. Sorry, that's not right. We had we had 9 I hats and we had 7 j hats. So 89 plus 49. 81 plus 49 is 130 square root of that, 130. Okay, and it's positive, notice. All right. Now, what if we unit vector u in the direction of vector r? All we need to do is then take vector r and divide it by the magnitude of vector r. That would give us this. Think about what that means, right? It's if vector r was like square root of 130 long, well then 1 divided by the square root of 130 would be the length of the unit vector. Okay? not 1 divided by a unit vector. If we wanted to, like this illustrates it pretty well right here, I think. Okay, if we have a unit vector u, what that's talking about is this vector right here, this little small vector of a unit length 1. Like the length of that is 1, right? Okay, that's vector u, and its magnitude is 1. The way we would find out what that unit vector was this. This isn't going to be super important, but this is the math for that. Okay, now we've talked about in this video, we've talked about scalar multiplication of vectors and just simple addition of vectors and finding the magnitude of vectors using the Pythagorean theorem. That's really it to find the magnitude of vectors. But most importantly is is hopefully the understanding that the 2 different ways we can represent vectors in kind of the mathematical way, where we have this notation and this kind of more physical way where we were talking specifically about just like a number of unit vectors in the x direction, number of unit vectors in the y direction, and combining that into this statement. This will be what we end up using like most often when we're doing applications of vectors, which is really the important part.